The next time you press two magnets together and feel that invisible resistance pushing back, pause for a second and really think about it. Because what you're feeling isn't just a neat trick of metal, it's one of the deepest forces shaping the universe, quietly working beneath every object you've ever touched. Flip one magnet around and suddenly they snap together with a sharp pull that feels almost alive, like something unseen just made a decision. So, what is that force? What's truly happening in that tiny space between your fingers? To answer any why question, you always need somewhere to stand, some basic truths you accept before you dig deeper, because if you don't, the chain of questions never stops. Imagine asking why someone ended up in the hospital. You might say they slipped on ice and broke a hip, but then comes the next why. Why did they slip? Because ice is slippery. That sounds obvious, but if you keep going, you realize even the obvious hides explanations. Ice feels slick because pressure from your foot melts a microscopic layer on its surface, turning it into a thin film of water you glide across. But that just pushes the question further back. Why does pressure melt ice? Because frozen water expands, and pressure tries to squeeze it back into a denser form. But why does water expand when it freezes? Now you're talking about molecular structure, atomic forces, and the strange behavior of one of the most important substances on Earth. You see the pattern. Every explanation opens another door. Gravity explains why a fall happens. Biology explains why injuries hurt. Emotions explain why someone rushes to help. Each answer is real, but none is the final stop. If you never choose a place to stop asking why, you'll keep digging until you collapse under the weight of endless questions. That's why people often want explanations in terms of things they already understand. They want the unknown compared to something familiar, something simple. If I told you magnets were connected by invisible rubber bands tugging them together, it might feel satisfying for a moment. You'd picture it, nod, and think you understood. But then you'd ask why rubber bands pull back when stretched, and suddenly we're right back to molecular forces, which are electrical in nature, meaning we're using the same mystery to explain itself. That isn't understanding. That's just a clever story. Electric and magnetic forces aren't explained by something simpler underneath them. They are the foundation. They're the bedrock we use to explain everything else. Chemistry is nothing more than atoms interacting through electromagnetic attraction and repulsion. Biology rests on chemistry, which means every living cell depends on these forces. The chair supporting you right now isn't solid because of some magical substance. It's solid because the electrons in the atoms of the chair repel the electrons in your body. Even your body holds itself together through these interactions. Everywhere you look, electromagnetism is running the show. Here's the funny part, though. You don't find it strange that your hand stops when it meets a table. You've experienced that your whole life, so it feels normal. But in reality, your hand never truly touches the table at all. The atoms approach each other. Their electrons begin to repel, and that resistance is what your brain interprets as touch. It's the exact same force at work when magnets push or pull, yet the table seems ordinary while the magnet seems mysterious. The only difference is familiarity. You stopped questioning the table years ago, and when you look closer, electromagnetic forces aren't just strong, they're unimaginably powerful. Compared to gravity, electromagnetism is stronger by an absurd factor, something like 1 followed by 40 zeros. It's so large that our brains barely know what to do with it. Yet we don't notice that overwhelming strength because atoms are built with balanced charges. Positive charges sit in the nucleus, negative ones surround it, and most of the time they cancel each other out perfectly. The strongest force in everyday life hides in plain sight because it neutralizes itself. Still, it occasionally reveals itself. When you run a comb through your hair and tiny scraps of paper jump toward it, that's just a handful of electrons shifting from one place to another. A minuscule imbalance, yet the force is so immense that even that small change becomes visible across the room. Magnets, however, are special for another reason, and that has to do with what happens inside materials like iron. Inside atoms, electrons don't just sit quietly. They spin, each one producing a tiny magnetic effect. In most materials, those spins point in random directions, canceling each other so completely that you never notice them. But in iron, something remarkable happens. Large groups of electrons line up, all spinning the same way, reinforcing one another instead of canceling out. And when that cooperation builds across billions upon billions of atoms, the hidden force suddenly steps out into the open, becoming strong enough for you to feel in your hands. And when that cooperation builds across billions upon billions of atoms, the hidden force suddenly steps out into the open, becoming strong enough for you to feel in your hands. That's why iron can become a magnet, while something like copper cannot, even though both are made of atoms with electrons and the same fundamental ingredients. The difference isn't the particles themselves, it's the way they organize. In copper, the electron spins point in all directions, canceling out their tiny magnetic influences. In iron, many of them align, reinforcing each other so their combined effect stretches beyond the surface of the material. It's a bit like a stadium full of people. If everyone talks at once, the result is just noise. Nothing clear travels far. But if that same crowd chants the same word in unison, the sound carries for miles. The voices didn't change, only their coordination did. Inside a magnet, electrons behave in a similar way. Their shared direction turns countless tiny effects into a single powerful one. But let's go deeper than that picture, because at the most fundamental level, magnetism isn't really about spinning balls or coordinated crowds. It's about interactions between particles, exchanges happening constantly at scales far too small to see. Electrons don't simply sit in place. They're always interacting, always influencing one another. In the language of modern physics, they do this by exchanging photons, tiny packets associated with light. Now, these aren't the photons you see streaming from the sun or glowing from a lamp. These are what physicists call virtual photons. They exist only during the interaction itself. You can't catch one or observe it directly because it isn't a permanent particle flying through space. It's more like a bookkeeping device nature uses to carry forces from one place to another. One electron emits a photon, another absorbs it, and that exchange produces what we interpret as attraction or repulsion. So when you feel two magnets pulling together, what's actually happening is an unimaginable number of these exchanges taking place at once. Trillions upon trillions of virtual photons pass between the electrons in both pieces of metal. Each exchange contributes a tiny push or pull, and together they create the force you feel in your fingers. It may sound abstract, but that's the simplest description we have of what's really happening. In fact, everything electromagnetic can be reduced to just three basic actions. A photon moves from one place to another. An electron moves from one place to another. Or an electron emits or absorbs a photon. That's it. From those three simple processes emerges all of chemistry, all of electricity, all of magnetism, every radio signal, every flash of light, every color you see, and even the fact that your hand stops at the table instead of passing through it. There's no hidden machinery underneath, no gears or springs or invisible strings. Those three actions are the mechanism. If you're tempted to ask what lies beneath that, what makes photons behave the way they do, physics doesn't offer a deeper mechanical picture. That's as far down as our understanding goes. It's not a placeholder explanation. It's the foundation. Back in the 19th century, scientists discovered the mathematics that describes these forces with astonishing clarity. In 1873, James Clerk Maxwell wrote down a set of equations that unified electricity and magnetism into a single framework. This wasn't just another scientific result. It transformed the world. Once it became clear that electric currents produce magnetic fields, and changing magnetic fields produce electric currents, humanity suddenly had the key to controlling energy in ways never imagined before. Think about what that means in practice. Somewhere far from a city, water falls through a dam, spinning a turbine. That spinning motion turns coils of copper near iron structures, and as they move, electrons inside the wire begin to flow. That movement travels through miles of copper lines, stretching across towns and streets. At the other end, another coil and magnet convert, that flow back into motion, light, or heat. Every motor, every light bulb, every appliance comes alive because electrons are moving in response to magnetic fields. All the wheels in a city can turn because one wheel at a dam is turning. Stop that one, and the others fall silent. Start it again, and the entire network wakes up. And what connects them? Not magic, not some mysterious fluid, just copper wire and iron shaped in the right way. That's the beauty of electromagnetism. Nature provides a simple rule, and from that rule, we build entire civilizations. What's even more remarkable is that we can calculate these effects with extraordinary precision. Using only those three basic actions of electrons and photons, physicists can determine exactly how magnetic an electron should be. They don't guess or approximate loosely. They sum every possible interaction, every path a photon might take, every way the exchange could happen. The result is a number predicted entirely by theory. Then experiments measure what nature actually does, using incredibly sensitive instruments. And when theory and experiment are compared, they agree to a level so precise it's almost absurd. The difference between prediction and observation is so tiny, it's like measuring the distance from Los Angeles to New York and being off by less than the thickness of a human hair. No other scientific theory matches reality with that level of accuracy. All of that precision, all of that predictive power, comes from understanding the electromagnetic force, the same force you felt as a child pressing magnets together at a desk or kitchen table. All of that precision, all of that predictive power comes from understanding the electromagnetic force, the same force you felt as a child pressing magnets together at a desk or kitchen table. We can describe magnetism with astonishing accuracy, predict exactly what it will do, and build entire technologies around it. But when it comes to explaining why this force exists in terms of something simpler or more familiar, physics reaches a boundary. It's not that scientists failed to dig deeper. It's that electromagnetic interaction is already one of the basic ingredients of reality. It's the thing other explanations are built from. There's a number hidden inside the mathematics of electromagnetism that nobody has ever managed to explain. It's roughly 0.085, or if you invert and square it, you get about 137. This value determines how strongly charged particles interact. It sets how powerful magnets are, how tightly electrons bind to atoms, how chemistry unfolds, and ultimately how matter holds itself together. Everything from the glow of stars to the structure of molecules depends on this number being what it is. But here's the strange part. We didn't derive it from something deeper. We measure it, we use it, and it works perfectly in our equations. Yet we don't know why nature chose that value instead of another. If it were dramatically different, atoms might not stay intact, chemical reactions would behave differently, and the universe could look nothing like the one we inhabit. Life as we know it might never have formed. So this single number, quietly embedded in the laws of physics, shapes the existence of every magnet you've ever held and every atom in your body. And still, its origin remains one of the great unsolved questions in science. The history of trying to understand these forces also reveals how strange the journey has been. When physicists first attempted to calculate the magnetic properties of electrons using early quantum theory, the equations didn't give sensible answers. Instead of finite numbers, they produced infinities. That's not a useful prediction. Infinity doesn't tell you what will actually happen in an experiment. For years, this problem stood in the way of making meaningful calculations. Then, in the late 1940s, a new idea emerged. Instead of treating the electron as an isolated object, physicists realized that what we measure is always the electron, along with all its interactions with the surrounding electromagnetic field. Those countless exchanges of virtual photons aren't optional details. They're part of the particle's measurable identity. By redefining the quantities in the theory to match what experiments actually detect, the infinities could be absorbed into those measured values. The results became finite, precise, and incredibly accurate. This process is known as renormalization. To some people, it sounds suspicious, as if scientists are sweeping problems under the rug. But the astonishing agreement between theory and experiment suggests otherwise. Whatever philosophical discomfort it creates, it works. And in physics, results that match reality carry enormous weight. Yet even with all this mathematical success, our intuitive understanding lags behind. The world at the quantum level doesn't resemble the everyday world our brains evolved to navigate. We understand rocks, trees, and moving objects because our survival depended on it. But electrons don't behave like tiny billiard balls circling a nucleus the way planets orbit a star. That picture is a convenient simplification, not the truth. Sometimes people say electrons are waves. That's not quite right either. Others describe them as clouds or fogs of probability. Those metaphors help a little, but they still miss something essential. The deeper you go, the less familiar the behavior becomes. If you want a clear visual image of what an electron is doing inside a magnet, something you could picture like gears turning in a machine, physics simply doesn't provide one. What it gives instead is mathematics. We write down equations, solve them, and those solutions predict outcomes with extraordinary precision. It's almost like having a machine that performs flawless calculations about the future without needing any mental picture of what the process looks like. It tells you when something will arrive, how strong a force will be, what pattern will appear, but it doesn't imagine shapes or colors or moving parts. It just computes. That's how our understanding of magnetism works at its deepest level. We can calculate what magnets will do with astonishing reliability. We can predict how electrons interact, how fields change, and how energy flows. But the ability to visualize the process in familiar terms remains out of reach. Nature at that scale isn't just smaller than everyday life. It behaves according to principles that have no direct counterpart in our daily experience. And that realization brings us back to the original moment of curiosity. You press two magnets together, feel that invisible push or pull, and ask what it really is. The honest answer isn't a metaphor about springs or strings. It's that electrons are exchanging virtual photons, that spins align in certain materials, and that the electromagnetic force is shaping the interaction. We can describe it with breathtaking precision. We can build machines and entire infrastructures on top of it. But when you ask for a simpler picture grounded in everyday objects, there isn't one waiting underneath. Those everyday objects are already explained by the same force. Magnetism isn't some strange exception to the rules of nature. It is the rule, quietly working everywhere, all the time. The push you feel between magnets, the resistance of a tabletop against your hand, the way your body holds together, all come from the same underlying interaction. Magnetism isn't the mystery that needs explaining. Magnetism is part of the explanation for almost everything else. It's one expression of the electromagnetic force, one of the fundamental forces shaping reality. Every atom in your body is bound by it. Every chemical reaction depends on it. When light reflects into your eyes and creates color, that's electromagnetism. When you feel something solid, that's electromagnetism. When a compass turns toward the north or a motor spins in a machine, it's still the same force playing out in different forms. And at its deepest level, it all comes back to those three simple actions. A photon moves from one place to another, an electron moves from one place to another, or an electron emits or absorbs a photon. From those three processes emerges chemistry, biology, electricity, magnetism, the structure of matter, and the stability of the world you move through every day. There's no hidden clockwork underneath, no deeper mechanical picture waiting to be discovered. This is how nature operates. What makes this even more remarkable is how precisely we can describe it. The equations predicting electromagnetic behavior don't just give rough estimates. They match experiments to astonishing accuracy, sometimes out to 10 decimal places. That's like predicting the distance between two cities and being off by less than the thickness of a hair. This isn't philosophical speculation. It's tested, measured, and confirmed over and over again. When the numbers agree with reality that closely, physics considers the explanation solid. But that doesn't mean we understand everything. That mysterious number tied to the strength of electromagnetism still has no known origin. We can't visualize electrons in a truly accurate way at the quantum level. Our equations work beautifully, yet our mental pictures remain approximations. And that's okay, because physics isn't about waiting until every question feels intuitively comfortable. It's about learning enough to predict what happens, testing those predictions, and using what works. The electrical grid powering cities runs because we understand electromagnetism well enough. Not perfectly, but well enough to harness it. The lights, machines, and communication systems surrounding us all rely on electrons moving through wires and fields interacting across space. Entire civilizations function because we learned how to cooperate with this invisible force, rather than needing to fully picture it. When you first asked why magnets attract or repel, what you really wanted was an explanation using something familiar. Rubber bands, springs, invisible strings pulling things together. But the deeper truth is that magnetism is the familiar thing. You've been experiencing electromagnetic forces every moment of your life. Every time you touched a surface, picked up an object, or felt your feet against the ground, that same force was there. Magnets simply make it obvious. They let you feel across empty space what usually only happens at microscopic distances. They reveal openly what is normally hidden inside matter itself. Instead of being mysterious, they're actually one of the few times nature shows its workings in a way you can sense directly. So the next time you hold two magnets and feel that pull or resistance, don't think of it as some odd trick of metal. Think of it as a glimpse of the structure of the universe, a moment where the same force holding your body together stretches outward and makes itself known between two pieces of iron. What you're feeling isn't magic. It's the same interaction shaping atoms, chemistry, light, and life. And the fact that we can describe it, predict it, and build a world on top of it isn't mysterious either. It's simply what happens when we pay close attention to nature, measure carefully, and write down what we see.